gives me great pleasure to introduce Gustavo Deco at the Pompeu Fabra University in Barcelona. Gustavo is an absolute pioneer in the field of brain connectivity, systems neuroscience, the dynamics approach to understanding the brain, which is by now taking the world by storm, and most importantly, linking all of this into the manner in which we think and behave. So over to you, Gustavo. Very excited to hear your presentation, Turbulence-like Dynamics in the Human Brain.
Yeah, thank you. Thank you, Mike, for the kind introduction. It's always a pleasure to be at the Brain Connectivity Workshop, even if it's by Zoom. It's a new experience. Mike already mentioned the title. This is a common work with Morten Krinkelbach, and it's pretty novel. There is only one publication, and most of the message that I'm trying to transmit here is even not published, so it's very good, I think, for discussions. So let me start with a slide with motivation. So why the hell we got interested on turbulence in the context of brain dynamics? I mean, turbulence is very interesting in the context of physics, in the context of fluid dynamics, but there is no link actually with or intuitive link with neuroscience. And there are three motivations that I try to explain here in this first slide. The first motivation is historical. Actually, the first person that was wondering about the beauty and the complexity behind the turbulence regime in fluid dynamics was Leonardo da Vinci. In fact, he introduced the word turbulence in Italian, that came from Latin, turbulentia, from turba, meaning crowd, which is what he tried to capture, and this is the reason why he considered turbulence dynamics extremely beautiful, is this mixture between order and disorder. So there is a lot of stochasticity, but also is beauty enough because there are many ordered patterns like those wheels, those eddies that he trying to capture. And this mixture between order and disorder is something that we have also in our brain signals nowadays in neuroscience. That was the first motivation. And that is reflected in this movie where we see a typical turbulent dynamics in a fluid and those eddies with different size, which are somehow hierarchically organized. The beauty is that, of course, after many centuries of developing theories in neuroscience, in physics of turbulence, people were able to derive the Navier-Stokes equations, which is basically the microscopic way of expressing fluid dynamics. And this is the second motivation, because there is a parallelism with the neuroscience. We have the microscopic equation, we have the microscopic equation, we have the microscopic phenomenon, in this case, turbulence in the context of fluid dynamics. In our case, we have the microscopic equation, which are the Hodgkin-Huxley, and we want to understand the emergence of interesting brain function or interesting macroscopic dynamics. And of course, this is not happening, and it's very difficult to achieve that. And that was realized also in turbulence theory by this guy that appeared in the movie. Richardson is there because he discovered and discovered qualitatively and even poetically, with a nice paraphrasing of the original Jonathan Swift's poem, that there is a hierarchy in those patterns, in those eddies and wheels across space. And this is related with a very efficient transmission of energy. That was translated by Kolmogorov in mathematical terms later on, and that is the last motivation, the efficiency. So that's, if we renounce really to describe everything from the microscopic point of view, and we concentrate on the statistics of what Kolmogorov called the phenomenology theory, on the statistic at the macroscopic level, then we can discover very rapidly that there are many power laws which are reflecting a very extremely efficient transmission of information across space and time. And funny enough, he introduced a concept that is called a structure of function, which has nothing to do with what we call a structure of function in neuroscience, but it's related because if you see the definition, it's just the average across space and time of your signal. In other words, will be the Ball signal. In fluid dynamics is the velocity as a function of the Euclidean displacement, the distance. And this is basically a cosine of the functional connectivity. And he was showing that this functional connectivity in our language was showing a power law as a function of the distance, and this is related with the effective transmission of information. So that are the motivation. So the first step is really to show, independent of any models, so just taking empirical data, and for that we focus with Morten on the first step on the empirical data of the HCP, of the Human Connectome project. So we consider whole brain data, Ball signals under first under resting state conditions in a group of more than 1,000 people. And the key idea in order to show turbulence in a context which has nothing to do with fluid dynamics was actually following the steps of a great scientist, which is Kuramoto. Kuramoto studied in 2017. He published a very beautiful paper where he studied a system of what he called non-locally coupled oscillators. So this equation is very simple. The first part is just describing the oscillator. In this case, are Stewart-Landau oscillators, or what we call also Hopf oscillator, and they are coupled in a ring. And the coupling function is very simple. It's just an exponential distance rule. And when you have this, he studied this system because this system is showing turbulence. And the way how we managed to show this turbulence, which is totally different from the type of turbulence that we characterize in fluid dynamics, was by using a generalization of the Kuramoto order parameter. As you know, the Kuramoto order parameter that we use also many times in the context of neuroscience is just the sum, in this case, because it's continuous, it's just the integral of the exponent of the imaginary part of the phases, in our case, the phases of the Ball signals. And as you know, the module of that is between 0 and 1. 0 means that is not synchronized, 1 that's extremely synchronized. Well, we can relax that, and we include now in this summation the kernel that we use for the coupling, so this exponential distance rule. And this is what we call, or what Kuramoto called, the local Kuramoto order parameter. And the module of that is also a measure of synchronization, but now locally in time and locally in space. And in fact, if you do the simulation of this ring of Stewart-Landau oscillators as a function of space and time, and you plot in color the module of this local Kuramoto order parameter, what you see are these kind of variation across space and time of the local synchronization. And those are basically like the wheels or like the eddies that we saw before in the context of fluid dynamics. In fact, he defined a turbulence, a particular type of turbulence, which is technically called amplitude turbulence, as a system that shows high variability across space and time of this local Kuramoto parameter. So basically, if you take the variance, for example, of this local Kuramoto parameter across space and time, and this is significantly different from 0, then you have turbulence. So we took the 1,000 people of the HCP, the Ball signals, we calculated basically the Kuramoto, the local Kuramoto order parameter, we calculated the variance, which is what is plotted here. Of course, we contrast this with appropriate surrogates, and basically in this set of data, this massive large set of data, we see that there is a very significant value of this turbulence. In fact, we can do a kind of similar diagram as the one of Kuramoto, just by reflecting the Kuramoto order parameter, so the air, as a function of time, so for different snapshots, rendered in a flat brain, and as a function of space. And as you see, it's very similar to this toy example from Kuramoto, where we see that across time and across space, there is a large variability of the local level of synchronization which reflect the eddies. So the second step is really to try to understand that now from a mechanistic point of view. And for that, we use Holberg model. The beauty is that we can use a Holberg model that we defined it some years ago together with Petra, Victor, and Morten, which was basically using a Stewart-Landau oscillator. And it was a nice casualty and was very good. We use this in many different contexts, and this is what we use here. So basically, it's the link between the anatomy through the local dynamic of Stewart-Landau oscillators in order to reflect the macroscopic dynamic. But the particularity here is that the anatomy will be reduced because we want to analyze the minimal terms which are necessary in order to sustain a turbulent core. And what we, in fact, are using is a discovery, a crucial discovery from the lab of Henry Kennedy in Lyon by massive track tracing studies in monkeys. That was also later on done in mice, is now done in a marmoset. And he discovered a very simple anatomical rule, namely that the number of fibers are homogeneous and isotropic, and it's only dependent on the distance. How? With an exponential distance rule. Again, another causality, very similar to the kernel that Kuramoto was using in the slide that I have shown you. So here, instead of using as traditionally the tractography, the structural connectivity, we generate the structural connectivity by fitting, in our case, the MRI tractography of the humans in the HCP with an exponential distance rule, which is, by the way, it's also interesting to see. And I think it's the first time that someone analyzed that. That's the tractography, the fibers density in humans are also following an exponential distance rule. This is the first change. The second change, instead of using here the traditional observables like functional connectivity dynamics, metastability, we use the structure functions, which is basically the functional connectivity, but as a function of the distance. And in fact, we have only one parameter, which is the coupling parameter, and we see that as a function of this coupling parameter, there is a working point. So the blue curves is really the level of fitting of the structure function of the functional connectivity as a function of the distance, and there is a minimum. So this is the working point. We fit the data. At that working point, then we see that the level of turbulence that we saw in the data, which is reflected here with the dashed line, if you remember, was around 0.19, the empirical level of turbulence is also fitted with the red curve, which is the level of turbulence of the model. And it's not only fitting exactly at that point, but it's also maximal. And then we started to speculate that because it's maximal, then turbulent, which is sustained just with this minimal model of the underlying exponential distance rules in the anatomy, has some particular properties. And in fact, if you check some information properties like sensitivity, that's what we call susceptibility, or how we encode the sensitivity to external perturbation, they are maximized exactly at that working point, and probably because of the a large amount of turbulence. In fact, in that working point, this is a particular subject of the HCP, and you see now in a movie the evolution of the local Kuramoto of the parameters, or the evolution of the local level of synchronization in a space and time, in a 3D rendering and in a flat plane, and the same in the model for the optimal working point, and you see really the similarity of these of both dynamics. So with that, we have done many things, but I wanted to stress here, and just to finish my introduction and my talk, at least with the slides, a very crucial question. So we concluded that the minimal requirements for sustaining turbulence, that apparently is extremely important for getting this efficient transmission of information across space and time, is exponential distance rule. And then I heard many times Henry Kennedy, and he always stressed that the most interesting part of the exponential distance rule is not the exponential distance rule, are the exceptions. And there are really a very small amount of exceptions to the exponential distance rule, which are in general long-range exception. This is what he called the rare long-range exception. It's around 1%. And we found also those exceptions in the tractography of the human data in the HTTP. And the key question that we are trying to formulate here is, what are the roles of those exceptions? As I say, minimal, 1%. This is like the small world business where we have here in this cartoon, in the ring version, the exponential distance rule. And on top of that, we have those exceptions, which are really very rare. So we know that topologically at the structural level, they have a nice property, but now we are asking really for the functional properties. And of course, we cannot do this experimentally because we cannot study these two systems experimentally in the brain. But by doing a model, which assume only the exponential distance rule or the exponential distance rule with the LR, so meaning practically the full tractography, and so the full structural connectivity matrix, we will see that we can analyze special properties, for example, the functional connectivity, but only limited to the long range, or how the information is transmitted. For that, I use the concept of information cascade, and also the level of turbulence. And the main result is here. So after fitting both models, the model with and without the long range exception, of course, the model with the long range exception is better. This is trivial. This is expected because we insert more information, so it's a double check that it's okay. The level of turbulence is not changed at all respect to the surrogate. It's perfectly fitted in all the models. But here at the bottom in these two graphics, we see that these two important properties, so how correlation is really transmitted at the long range, or how information is transmitted across a space-time in an efficient way, are really significantly increased only through the long-range connection. And the last question that I want to formulate is my last slide is this: why is that? This happen always because we have this long range on top of the exponential distance rule, or has to do with the underlying dynamics? In order to study this, we go to the ring of Stewart-Landau oscillators as studied by Kuramoto. We include three versions of nearest neighbor, the exponential distance rule, and the exponential distance rule plus 1% of long-range exceptions. And in fact, we studied exactly the same observables, these two desirable properties, how good the information and the correlation at the long range is transmitted, and just concentrate on the blue and red condition, which is the exponential distance rule and the exponential distance rule plus long-range exception. And as you see, is that, and it's the beauty of the ring here, we can regulate the level of turbulence. And in fact, in this condition, in this panel, the middle panel, we have low level of turbulence. In the bottom panel, we have high level of turbulence. And we see that this increase or the effect of the long-range exception are really clearly amplified because of the underlying turbulence. And this is the main conclusion, that this turbulent core is really important, because if we don't have this turbulent core, then the long-range exception, they don't have such a huge impact. I think that is basically in a very brief form, of course, what I wanted to say about that it's very useful to use concepts and methodology from turbulence theory, that in fact those concepts are not only useful for understand better the brain with those tools, but the brain show a really dynamical characteristic which are remember as really fluid dynamics, and the reason is because of the efficiency in the transmission of energy and information. So thank you for your attention, and I'm ready now for the discussion.
Gustavo, thank you. This was a beautiful talk and very intriguing work. So beautiful way to kick off the day too. While I guess people formulate their questions, it's intriguing evidence for these highly non-stable nonlinear dynamics. And I think, as you beautifully show, a way of transmitting information sort of broadly conceived between different scales. Just given the theme of cognition and consciousness, I mean, how do you think this or what thoughts have you had on how this relates to sort of basic principles of action and perception? And in particular, is there a paradox between the instability of the dynamics compared to the relative predictability of behavior? I just
Yeah, it's a very good question. Thank you, Mike. I mean, actually, this turbulent core, sustained by the underlying exponential distance rule, is like it's like the most basic type of resting state. In fact, we were showing that, I think is somewhere here. I have the slide. Yeah, here. We were showing that another effect of introducing this long range on top of the turbulent core is the building up of the resting state networks. And as you know, the resting state networks relate with concrete functions, with cognition, with perception, and so on. So from that point of view, what I believe, or the way how I interpret that, that's the turbulent core. It's of course, which is a kind of instability, of course, but it's a kind of instability which is extremely good for this information processing and for transmitting in a very efficient way, meaning power law, information in form of local synchronization from one side of the brain to the other side and across time. But of course, it's not useful per se. But if on top of that, we connect the long range, and the beauty is that we don't need a large amount of long range, just a very small percentage, then the next step is to build up the resting state networks, and we build up the resting state network, the classical one, the full mode network, silencing network, limit, and so on. And by having that, we have the basis for the ability to perform cognition and perception. So I think there is the link that that you mentioned. So that's in this, the instability is only for the background.
Okay, so behind the apparent instability of these quite stable dynamical architectures. Now, I'll pass over, if I have mastered it correctly, to the Q&A box. I wonder why some of them have popped over to answered. Oh, Randy, you have the panel privilege, so fire away.
I have my pale hand up there.
Okay, yeah.
Gustavo, that's very fascinating talk. I was delighted to see this as the starting of the session today. I've got a methodological question and then sort of a relationship question. Yeah. So the methodological question is very easy, and I probably should have read the paper before I asked this question, but I just want to get a quick definition of what information cascade measurement is.
Yeah. Yeah, I give you, I skipped the definition on purpose because it's a little bit complex, but the idea, like always, is relatively simple. So what we calculate is the local Kuramoto order parameter at different scales. So meaning that in the kernel that we use the order parameter, we cover the different scales, meaning that we go from large eddies to very small eddies. And basically the information cascade is nothing else as the correlation across time between two consecutive scales. And then we do this for all consecutive scales and just integrate over all the scales. So the take-home message is basically it's the transmission of information in vortex space, what we call the vortex space, which is this local Kuramoto order parameter through correlations, and we try to consider all spatial scale. Therefore, I think it's a good measure. Yeah.
Yeah, it sounds very similar to, like, for example, there's a spectral entropy calculation that looks at entropy as a function of time scale.
Yeah, in fact.
Multi-scale entropy that I use a lot also does a very similar thing. But here, I guess it's dependent specifically on spatial distance. Is that correct?
Exactly. Yeah.
It's a nice, very nice complement.
Multi-scale characteristic as the spectral entropy. Yeah.
The second question has something to do, and I see Victor just put his camera on about the connection between the phenomena you're characterizing here in the brain and some of the older work on waves that are measured with EEG, traveling waves, for example, standing waves, and then there's the model that Paul Nunez put together, and I think it was the 70s, that also looked at sort of propagation of coherent patterns across the cortical surface, and whether these are sort of related phenomena, but at a different time scale or something like that.
Yeah, I can only speculate, of course, about that. I mean, it's a very interesting issue, and probably we are going a little bit in that direction because we got interested to try to generalize this in the context of MEG and also in the context of EEG. My intuition and my speculation is that this, of course, at least in resting state conditions, that is related, that those traveling waves are probably reflecting some underlying property of these vortices that were transmitting information in form of propagating the states of synchronization. Of course, at this point, I don't know because I never analyzed it with this methodology, still the EEG. One complication that we could have is that at least for analyzing this from the point of view of Kolmogorov with the Power's law and so on, is that we need really a relatively fine spatial resolution. So therefore, in this context, I forgot to say, we use the Schaeffer parcellation with 1,000 nodes in order to have real access to the distances. Perhaps that is not necessary for EEG because, and we use just the local Kuramoto order parameter and forget the propagation across a space, at least at the fine scale. So that could be a methodological complication, but perhaps it's doable. And as I said, my speculation is that I think it's at least under resonance and spontaneous condition should be related and reflecting exactly the same.
I think Victor has a follow-up comment. He's got his hand up.
Victor, you want to follow up with your comment?
Well, it's linked to this. Good morning, everyone. Good night, good day, good evening, depending on where you are. Yeah. Yes, I have a follow-up on this. Hi, Gus. Thank you very much for this beautiful talk. I heard it now, I think, once or twice before. And I discover more and more new questions. One is linked now to the issue of locality and also in reference to what Randy was talking about. I'll remind you that when you go back into the 90s, not into the 70s of newness, but in the 90s, there this exponential rule came up with Peter Robinson and with Harkin and myself, etc., because we didn't have connectomics available at that time. Mm-hmm. So we have made exponential approximations of the connectivity kernel, and what you call local is actually translationally invariant. Yeah. Yeah, let's be very specific because it can be actually large range, but translationally invariant. And there is the following point very often as you're making reference to the Kennedy data. And at that time, there was Almut-Schütz, for instance, mapping out the distance, the Euclidean distance with Valentino Breitenberg, of course. And it was exponential or can be fitted as exponential. But that's a one-dimensional representation, Gustavo. Yeah, 1D. It does not mean that the topology is rotationally invariant, rotationally symmetric. And in fact, it is actually not. Almut made a very strong point at that time that it's not rotationally invariant. Yeah, so that you have actually patchy distributions, patchy connections. Yeah. And when you map everything on the distance, it becomes nice exponential, yeah. But topologically, this symmetry is broken. And this has then led later to the postulate, actually, that we need a connectome, yeah. Because otherwise, you will never be able to estimate and approximate the spatiotemporal patterns that you observe. In fact, I have a 2001 paper in which we demonstrate that the error that you make with increasing mode and precision through an exponential distribution function does not go to 0, hence it's not an approximation. You're not making full use of this here. However, this issue, we are running into this also because you're looking at these structures occurring at a larger level. And I assume as a distance, you're always taking the distance between the nodes, between the vertices, right? Yeah. And there you're mapping the individual distances. So, and then you actually also connect them before you put in the exceptions. The way I understand it, you connect them in a rotationally invariant thing, just distance dependent. So there we are running into this issue. You're choosing a translationally invariant equation in order to have later the structure functions. This you do symmetrically. The exponential distance rule applies, so that's good. But then with the 1% of the long range fibers that you put in, you'll start manipulating it on the long range. However, there remains, which means you create structure through these long range fibers and a kind of more ordered structure through the fact that you have this translationally invariant kernel, which can be actually always approximated by a partial differential equation. This is what the translational invariance does. So you enter into the domain of, like you made reference to the Navier-Stokes equation, etc. So you have the capacity of doing this type of dynamics that on the large scale then you organize through this 1%. Sorry, this is a little bit a lengthy question, but I find this very interesting and intriguing here. The question is, how do you see that? Yeah, how do you deal with this aspect? Yeah, that you're overriding essentially the topology. Yeah, and then you have to obtain some type of structured on the long range because you have generated a spatial temporal pattern forming system, yeah, through this translationally invariant kernel, and then you start pinning it down on the long ranges. So it has to go into this particular direction. Do you see any problems there? Because when you go onto the real connectome, you don't have this particular symmetry. And once you start trying to fit actually patterns and not just the statistics, I would suspect that actually it would kill the precision of the work because you're not putting it in there. So there are multiple questions and it's a little complex, but I wanted to try to grab the essence of the pattern formation that you have in here. You see my point, Gus?
I think I saw your point, yes. So many comments. I mean,
yeah, that's a point.
From the point of view of the data of Henry, and also from the data that we analyze it from the tractography in the HCP, of course we were fitting those data assuming what you call translation, I call homogeneity, but it's the translation invariance, it's the same.
Same thing. Yeah.
I also assumed rotational symmetry. So in the model, I mean, we can discuss if this is okay or this is bad, but this is how I fit. So the model is really homogeneous and isotropic. So it has translational and rotational invariance. And with that, I do the best that I can. So I fit the fibers density in that large data set, and and as you saw, I said that's in the model. So it's this extremely simple function. The only thing that I fit is lambda, which, by the way, the lambda that you fit in the human is pretty similar to the one fitted in the monkeys. And that is so. Then we can discuss. Okay, perhaps we are missing a lot there. And in fact, we are missing a lot, but it's not so bad because that model, the level of error, of the quadratic error fitting functional connectivity, in this case, let's say functional connectivity, just to keep the story simple, it's very good. So meaning that the model is not so bad. But I totally agree. I mean, this is only preparing, and this is my interpretation, this is only preparing the minimal requirements for having an efficient transmission of information across space and time, and this is what I call the turbulent core. Of course, I need to break the symmetry. And the breaking of the symmetry, and for me that is astonishing, can be done by modifying a really small amount of connection. So I need to introduce those exceptions, but which are not many, and those are enough for radically changing, breaking the symmetry. And they are of course not improving so much the model, improving a little bit, but it's not surprising and also not fantastic. It's not changing the turbulent core, which is good because meaning we keep the same properties for transmitting information, but it's really improving some properties that we want to improve. Like for example, we want to really enhance long range connectivity, functional connectivity, or we want to transmit more information, or what I answered to Randy. I mean, we start to build or to make the resin-set network as the basis for being able to achieve then something concrete. One remark more. In fact, we analyze it also. It's in the paper. I didn't present it here, but we analyze it also the 7 tasks of HCP with this methodology, just for fun. And what we found is that basically the turbulent core is not modified. So because we fitted the power law explicitly in the structure function that I was not showing here, just as a question of time, but you can fit the power law in the structure function in resting state. And when you fit that in the 7 different tasks, so now people are doing really something, working memory, gambling, relational, emotion, social, blah, blah, blah. The turbulent core, the power law in that particular region is not modified at all, but the long range connections are radically modified. So, well, radically perhaps is an exaggeration, are modified. Probably thanks to this long-range connection, but just as an empirical fact, I mean, in this case, there is no model. That's an empirical fact that the core is maintained and the long-range functional connections are modified.
Yeah. In this sense, Michael, if I can just one follow-up comment. In this sense, I think you use the same architecture that we have requested in 2001. Homogeneous connections plus some long-range connections. Otherwise, you will never have the symmetry breaking. The only difference I see here is essentially the turbulence core, which is lovely. How do you quantify turbulence intensity? What was the metric that you used? Not the core. This is the structural part, but the intensity itself.
The intensity is the variance of the local Kuramoto order parameter.
The variance. So the structure function. Use as a structure.
The variance of the local Kuramoto order parameter.
Okay, thank you.
Okay, I'm going to go to the Q&A and then come back to Carl. A modified Bessel function of the second kind is, I think, the formal geometric rule in those old-fashioned neural field equations. But anyway, I was wondering, Andre Lupi, do you want to unmute yourself, or shall I ask?
Hi, thank you. This is really fascinating work. I just had perhaps a small question, but I was wondering how the local metastability that you were describing in the beginning relates to phenomena like the presence of chimera states in the spatial temporal functional data. Thank you.
Yeah, thank you. It's a very hot topic, not in neuroscience, but in turbulence, in fluid turbulence dynamics. So there are some papers during the last years trying to associate turbulence and exactly in the context of what you mentioned, in the context of the local Kuramoto order parameter, the metastability, with chimera states. So I can only do, I don't give you a concrete answer. I give you only 2 comments. I mean, there is literature on that, and people are trying to relate chimeras with turbulence, which is not astonishing. In the context of the exponential distance rules, perhaps I would call that chimeras. I have my problem with chimeras because I think people overuse the word chimera. I mean, chimera was introduced, and the key idea of the chimera is that you have a symmetric system, and the dynamic is not symmetric, and therefore you have a chimera. But if the system is not symmetric, then you cannot call chimera. And people start to use the word chimera for whatever really metastability you have. In this case, probably, and this is my second comment, in spite of my skepticism about chimera, probably there are genuine chimera in the, if you ignore, of course, the long range. So in the abstract model with the exponential distance rule, because it's a symmetry. It's what we discussed with Vic before. I mean, it's homogeneous and isotropic symmetry. And given that what we see is a very rich metastability, which is how we measure turbulence, we can associate that with chimera. So,
thank you.
thank you for the question.
Of course, I'm muted. I think, John, I think Gustavo nicely talked to these long-range connections. So if you don't mind, I'll jump over to Matteo Mancini. Do you want to unmute yourself, Matteo? Okay, I'll give it a go. He says, thank you for your interesting talk. Did I get it right that the exponential rule implies that the number of neurons, I think it's the number of synaptic connections away from neurons, decreases as a function of connection length? So that's correct. But the interesting part of this question is, do you have an explanation for why we don't really see these tracked tracing long-range connections standing out in the data, say, of Henry Kennedy, in the way that we do in the tractography data?
So again, I didn't get the last part of the question. What was the conclusion?
Do you have an explanation for why the track tracing trend seems to miss those additional long-range connections that you find in track? Okay.
Oh, no. That was a misunderstanding. I think, of course, the long-range connection was found by Henry. I mean, as I said, I mean, most of the connection follow this exponential distance rule, but he clearly found in track tracing studies in monkeys very clear long-range exceptions. And actually, he was always wondering about the role of those exceptions. So you can find those exceptions in the DTI, and of course, in a much better and reliable way in track tracing studies. This is a fact.
So lots of beautiful details in those connectivity works. An anonymous attendee asks, can I clarify if in this version of your model, the G parameter increases with turbulence? The G increase with turbulence is indeed increased turbulence in these models and not increased levels of connectivity as in some of your older models.
That's increased turbulence and not increase what? Sorry?
The G increase with turbulence is indeed, so this increase in turbulence with the increase in G beyond the minimum is increased turbulence and not increased levels of connectivity, as in some of your older models. I guess maybe to rephrase, where do you see the commonalities in this model? And where do you see some of the differences with prior work?
Yeah, to be honest with you, I don't understand. I mean, but I clarify this. I mean, clearly the turbulence increase and decrease also. I mean, it has a maximum as a function of the coupling parameter G. And the best fitting of the turbulence, as you see, compared to the empirical, is exactly at the working region when you use another other measures. So turbulence depend on the level of coupling, of course. I don't see nothing wrong with that. I mean, of course, I mean, and it's expected. I mean, all the dynamical properties will depend on the level of coupling, or so depend on the level of G. So the question is where you are consistent with the reality and which particularity has the turbulence at that particular state of the G.
Okay, yeah, thanks for clarifying that, Gustavo. Johann Peter Philippe Wards asks, I guess this relates both to the connectivity and to the dynamics, but are there any particular brain regions that seem to be host more than others to these long-range connections that stand out from the background exponential rule? And maybe also the dynamics. Are these chimera states or the highly turbulent dynamics more strongly expressed in some brain regions than others?
Yeah, it's a good question, and I don't know the answer of the first question. I mean that we just detected really the exceptions to the exponential distance rule, and we know that most of the exceptions are at really long range. We, to be honest with you, also we check it, the strength, at least in the tractography of those, so in terms of fiber density, and they were pretty homogeneous. I mean, I think there was a little peak really for the longest connection, so that there is a tendency to have in the exceptions to be even stronger the larger is the connection. But I don't remember, to be honest with you, but there is a figure in the new paper, which is still not published, but it's in bioRxiv. So that could confirm. But in general, I think there is no such a strong dependence. So the exceptions are exceptions in terms of the exponential distance rule, but not in terms of the strengths. I mean, with some particular bias, perhaps, and so on. And the second question was about chimera. I didn't remember.
Well, likewise, are the dynamics more turbulent in some regions than others?
No, as a dependence of the long range, he means probably, but this is what we were showing here. That's with or without long range, basically you have exactly the same level of turbulence, which was already good and was a very good fitting of the empirical one. So the long range exceptions are not modifying the level of turbulence. So the level of turbulence in this minimal model is basically only dependent on the G factor, on the global coupling.
Okay, thanks, Gustavo. So we'll end your hour with a question from Professor Carl Friston.
Oh, thank you. Although there are two unanswered Q&A ones, so I feel a bit guilty. Are you sure you want me to answer the question?
I thought we'd gone through them, but yes, Carl, please do ask.
Right, but it sort of comes back to your original question about, you know, what are the what is the turbulence for in terms of function? I think there may be an interesting answer, but I need to know from Gus the relationship between vortex and turbulence and the solenoidal or non-dissipative part of a Helmholtz decomposition of any flow. So, because if you looked at this as a decomposition of dynamics at any one point in the brain as a mixture of dissipative gradient flows and solenoidal irrotational flows, it seems to me as if you're looking exclusively at the solenoidal flow at many levels. You know, first of all, you're using phase loosely coupled phase oscillators, so the phase is just looking at the solenoidal irrotational part. And I presume that you're assuming that the bulk signal is just generated by that solenoidal flow. if that's the case, well, perhaps can I ask, is that the case? Is, you know, what are we looking at here is basically the symmetry breaking and the state dependency and the temporal and spatial fluctuations in solenoidal flow. Would that be a fair sort of summary of what?
I would agree. Yes.
So just asking Michael's question, what's solenoidal flow good for? That's my question. I've got two answers, and I want your judgment on them. The first thing is that just, you know, drilling down on what causes stochastic chaos. It seems to be exactly the symmetry breaking and the state dependent changes in solenoidal flow and not the gradient flow. So if you wanted to say, why is solenoidal flow or turbulence important? You could say, well, in the absence of that, you wouldn't get any mixing or stochastic chaos of the sort that sort of really augments any optimization or gradient descent scheme. So yes, there's gradient descent going on, but it is massively, if you like, enhanced in terms of an optimization scheme by having a stochastic chaos that is induced by that. That would be one answer. And one really trivial, well, you know, I'd like you to comment on that. But just a final thing that often comes up in my world in the context of the teleology of solenoidal flow, even at the level of a simple Kalman filter, you can actually look at the update before you start, sorry, the prediction before you add the update term on the basis of new information as the solenoidal part of the flow, because you're not, if you like, changing your beliefs or updating your state estimation in a way that corresponds to a gradient flow on some likelihood function, because there's no new data, but there's still movement. You know, the brain is moving to predict, you know, what I think will happen in the next instant, even the absence of actually looking at it. So I think from the point of view of the teleology, coming back to Michael's question, you could easily argue that without solenoidal or turbulent dynamics, you couldn't do predictive processing, for example. You certainly couldn't do Kalman filtering in the brain. But the first thing, I mean, the connection between the mixing and stochastic chaos and specifically the solenoidal part, or the irritational part, is that a thing in physics?
Yes, yes, and absolutely agree, Carl. I mean, and that is for me really the crucial point, and was actually one of the motivation. I don't know if I say that explicitly in my first slide, but the beauty of turbulence. Turbulence is a spatio-temporal chaos. In fact, in the literature in fluid dynamics, there is a discussion if spatio-temporal chaos and turbulence are two different things, or are the same or are the same thing. I mean, for me, it's really exactly the same. So it's a spatio-temporal chaos. And the beauty or the utility of a spatio-temporal chaos is exactly this mixing property. And because of this mixing property, which now in the context of turbulence, we can understand much better than in the context of general chaos. And I think this is the beauty of the Kolmogorov theory, of the Richardson interpretation of the hierarchical structure of the vortex and so on, because it's very intuitive. We have this mixing property implemented in turbulence in a very easy way, because you are transmitting and pushing energy. In the case of fluid dynamics, it's a kinetic energy from the larger eddies to the smaller eddies. So you have a perfect implementation of the mixing. So as you know, in chaos, we always have mixing properties. But in turbulence, I think we have a mixing properties implemented across space. And I think this is fundamental. And it's an extra properties on top of normal chaos. And for me, this is the crucial point, or was the crucial point, and the reason why we started really to study turbulence in the context of brain dynamics, because this is what we need in the brain, not in terms of energy, perhaps also in terms of energy, but I don't know, but in terms of information propagation, that we need this very particular implementation of the mixing properties, which is, I would call this, I wouldn't write that, but now between us, I can call that the hierarchical mixing properties. And hierarchical, I mean with this spatially ordering of of the effectivity of the mixing, which is reflected in all these power laws that we find in the data, also in the ball data, and that Kolmogorov found in fluid dynamics. So I think for me nowadays the word mixing and hierarchical mixing is the main properties that I like in all this business.
So do I. Hierarchical mixing. That's lovely. That.
Okay, that's on that beautiful note. I'd like to. It's a bit of a lonely clap when there's hundreds of people watching, but I'd really like to thank you very much, Gustavo, for this inspired presentation.
My pleasure. Thank you.
And this classically creative thinking of yours on a different perspective on brain dynamics. And in true brain connectivity workshop style, we ran out of time rather than ran out of discussions. I'm sure we could keep going. So thank you, Gustavo.
Thank you, Mike. And thank you all the people for asking so interesting questions.
Thank you.